everyone, as probably as you've seen, I've recently decided I'm going to learn about DeltaLake. And the first step of learning what is DeltaLake and how to use it is, in my opinion, look into the code and trying to understand how the things are built. I know a lot of people like to look into the examples, and I do too, and one of the great ways to understand the examples is looking at the code, and in the code there's usually the source code. In the source code there's going to be a main and test folders, and under the test folders we can see how exactly we can use DeltaLake. So let's get started. I downloaded the latest version, and you can see I already opened it with my IntelliJ. Let's change the view here. I've noticed it's a little bit quirky. Exit. There you go. Alright. So this is version 0.8.1 Snapshot. So it's not a final version. This is the version as we go that people work on in the community. And you can see this is the Delta core. So it's one of the 3 open source that Delta releases, and this one is its actual core. This is my home path, so don't pay attention to that. It's not related to Microsoft. Alright, so let's start with looking at the source. Like I mentioned, in every Java, Scala, whatever project, JVM project, there's always a source folder. And in the source folder, we're going to have all our source files. So you have main and you have tests. In the main, there's going to be the actual code of what consists Delta. And under test is going to be how we are testing Delta. And here we see we have 2 different libraries. One is Java and the second one is Scala. So these are code libraries. And then there are resources. And resources, just resources, to give you some different resources files, or everything we need is a resource to test our code. Alright, let's start by looking at the Scala one. And in the Scala one, I see 2 different folders, and most often the folders here are going to match under the test, going to match the name of the folder under the main. And the reason we use that when we struct the code, so it will be easier to understand where the things are, and also for the test. For testing, there's a lot of libraries who knows how to support that, the same hierarchy. Right, so Delta, we can look at tables. So we have 2 different classes. We have the first is DeltaLake suite, which is a testing suite, of course, and then the second one is Delta table test utils. And you see here there's an O, which means that's an object, and this is going to be a util class, which has one functionality, create table. Okay. And under the data table suite itself, so this is a class, Java or Scala class, and it extends query test. So let's look at the import to understand what query test is. And query test comes from org Apache Spark SQL, analysis exceptions, query test. Okay, that's something that builds into Spark SQL. So it's really the same tool that the folks here are using. With shared Spark session, yes, and Delta SQL command test. Delta SQL command test is a library being imported right here. It's part of Delta test, Delta SQL command test. All right, let's go over the test. For path, okay, that's the name of the test, with some temporary dir, because we need to import some data or some folders. Test data, and test data is an object. Okay, so it comes with SQL test data, write format data and save. So this is the actual functionality we would like to test out, and then we're checking the answer. So if this functionality happened the way we are expected it to be, then Delta table for path, there we go to df, and what is for path doing? We give it a Spark session. So this whole thing for path, so reading from this path, translating it to a data frame should be equal. We'll see what this answer, test answer returns. Test It doesn't return anything, but it's a unit, which means it can throw an exception. All right, going back. So this functionality can throw us back in exceptions. And you know, this is one of the way to test. So I'm guessing test data to SQL should be the same as, because test data is something that we had previously, should be the same as when we read it from the data frame, which shows that the right functionality happened and it's okay. Second one is same one, but here you see the difference is that we don't give the Spark session itself, which means that it should be somehow encapsulated already, and so we can read without being dependent on Spark session. However, when we write, it might be that we're still dependent on Spark session. We don't know exactly here how it works yet. All right, testing. For path with one delta table path, and the messaging is some string, well, not a delta table. Okay, with temp table, so for every directory, for every file in the directory, what we're going to do is test data write format with overwrite mode and the get absolute path of the directory, and then tests if the error message, not a delta table, equals the for path that we get when we try to get the path from it. And the second thing here, doing the same stuff only without the Spark session. So here we already know from the testing, if this testing passes, we know that we don't need a Spark session in order to read from a delta table. Okay, let's see. Oops, cancel. I want to run this testing suite. So it's going to take a while for it to build. I also notice I need to import some changes. So apparently I pulled some new changes and I need to import and start running with it. But this is just one of the ways I like diving into the code. I first trying to understand the testing, and then I'm slowly going into deeper and deeper into the source code. Because once I understand the testing, I'm starting kind of to get a feel of the objects, what is in the system, what is expected. Yes, okay. Import, I see a lot of errors. Yeah, please import changes and compile and do all the great things you need to do before we can actually start running it. All right, cool. So we saw this testing, and this is for the parser one. Let's see what else is fun. Oh, yeah, it jumped me into the source code. No, it was into testing. For path with delta, with non-delta table path, checking the message, and this is test for name on non-delta name. So with non-delta table name. Interesting. So that means I'm writing in the bucket with overwrite mode. So everything there is being overwritten, even if there's the smallest, only one file is going to be override if it has the same name, save as table, not delta table. Okay, that's an interesting name. And test for name on non-delta table. What does this functionality do? Okay, it basically calls itself this one. Test error message. For name, take the Spark session, table name. I'm testing if it gets its message back. And for name, just once again, with the session, Spark session, without the Spark session. And the test error, yes, it gets expected messages, and it returns a thunk to a unique unit. All right. Or it can get also a thunk to a unit. Yeah, this is the Scala fun part, when you can actually send implicit object, or you can divide the objects that you're sending to the function. Intercept, okay, analysis exception, to unit, and assert get message contains to lowercase. Right. So basically asserting is the message is correct, and this is not a delta table. And what we did, yes, because this test is it's not a delta table because the format that we use here is Parquet. And we know already that when we use the format of, there you go, test data.write.format delta, then it's a delta table. Otherwise, it's not. All right, cool, very cool. What else can I learn here from the different test table suits, test error? Okay, what is this? Test. All right. Delta table is Java serializable but cannot be used in executors. If it sounds familiar to you, you've been probably working a lot with Apache Spark. One of the challenges always, and when we try to create new classes, but we forgot about the serialization, and we're trying to send them to the executors, but oh boy, they're not serializable. It's not going to go over the network. So yes, this test is going to test out what's happening if delta table is Java serializable but cannot be used in executors. And this is an interesting one. Let's see. All right, so let's see how they're testing the serialization. Delta table can be passed to executors without method calls. Can it? It's very interesting. So we have a write format to delta mode save. So there's some writing going on here, and then the delta table. So we wrote in the delta format, and now we're reading it. We already know how it looks like, and this object actually encapsulates a delta table. So this is a delta table class type object that we're using here. And here we're calling Spark range, and Spark range creates a data set. Yes, all right, so it runs from the range from 0 all the way to the end. So from our case, it's all the way to number 5. Treated as long, right? So everything in the data sets, every object in the data sets are going to be treated as long. And then we're running the mapping functionality. And in the mapping functionality with Apache Spark, when we're mapping a data set, or when we're mapping a data frame, or when we're mapping an RDT, depends how low level you're going with Apache Spark. It actually means this functionality are taking place inside the executors. And it's important because in order to run this functionality, all the objects inside need to be serializable. And if they are not serializable, we won't be able to access them inside. So here we're actually showing that for every row, which is a row is just one type of long because we know it's a number, we just created it. We're assigning DT to some foo, and since this one is working, it doesn't throw any exceptions, and then we're running some operations on the number row plus 3, so it'll be for the first row, first executor is going to be 0 plus 3, second executor is going to be 1 plus 3, etc., etc. So this whole mapping is taking place distributedly, and it shows that the DT itself, the delta table itself, can be passed to an executor without method calls. So here we're not doing anything on the object itself. And then we're calling count. Okay, this is already outside, but count, it's really important for us to run count because this is this is an action in Spark. So in Spark, we know we have transformation, we have some logic, but then without an action, it's not going to run. And for us to see that it's working or it's not working, we have to call an action. And the action here in this functionality, in this test, is the count. Without the count, this code will not run. So we are enforcing it to run using action functionality. Okay, so here they say this should be fine, but here delta table can be passed to executor, but method call causes exceptions. And this is because this is what this test is trying to show, that delta table is Java serializable, the object itself is serializable, but we cannot use it in executor. So it doesn't make sense to pass it to an executor unless you find some edge case. Yeah, that's on you how you want to use it. All right, so here they're saying there's going to be some exception and we're going to catch it. So how will we, all right, so let's go for the straight out for the mapping, because we already know this is what's going to happen in our executors. And here we're calling the df and we call it toDataFrame. So this is already an action and a functionality method call inside the executors on DataFrame, and this is something we cannot do. Okay. And so we do we try, but already here we're supposed to fail, and this is all supposed to fail, and we're going to get an exception message. Should be delta table cannot be used in executors. All right, so here we're validating that this exception happens. All right, cool. Now that we know a little bit how the delta table suit work, we know it tests various of delta functionality. So if there is a delta table suit, there's probably going to be similar to delta itself. And we did notice there is an object named DeltaLake. So let's DeltaLake delta dt. Yes, here is dt. I'm going to click on it so we can start looking at what's going on in the source code. Okay, so what I said, evolving. All right, main class for programmatically interacting with delta tables. You can create delta table interfaces using static methods for path. So this is how we create delta table instances, and this is in 0.3.0 version. Perfect. It's encapsulated under private table, so this is a static private Scala annotations, and it's evolving. It's part of the annotations from Apache Spark, which means this class is going to be evolving. We have a transient object, data frame. It holds a data set. So now if you're familiar with Apache Spark and how things happens underneath that you know here that there's a data set. So delta table holds data set, which is a more progressed version of data frames themselves. All right, and second one, delta table version 2. So it means there is something that is version 2, but you can see here delta table version 2 is actually part of delta catalog. All right, so we'll need to dig a little bit into it because there is something with version 2 that I saw in the past in the Apache Spark code itself. Delta table operations, it's extended, that's great. And Scala. So let's look at the delta table operations, what it actually means. It's extend analysis helper. An analysis helper comes from Spark SQL delta util. So, okay. And this is an interface to provide an actual implementation of delta table operations. All right, execute delete, execute history, execute generate, execute update, execute vacuum. This is one of the functionality. Column map, Spark session. Of course, it has a protected Spark session inside. All right, let's look at the class itself. You receive a data frame, and as you can imagine, it can be null. Has as, it's evolving. This is for the SQL operations. Alias to data frame and just returns, most likely returns the data frame itself. Okay, vacuum. Yes, execute history, history. All right. So this thing holds a lot of the functionality. And you know what? Now let's see if it has, right. Oops. So I'm going to search for lighter version. Upgrade table protocol. DeltaLake holds protocols. And here it is, DeltaLake. Alright, I was curious about the DeltaLake because I know it's basically the tables transactions and all the operations transactions, and I want to know, this is like part of our blog post series that I hope you enjoy reading, and this is a part 2 where we talk about the DeltaLake itself. Alright, and DeltaLake is under IO Delta under tables. Under tables there's execution, there's Delta merge builder, and there is Delta table and DeltaLake. Alright. So DeltaLake is part of the Spark SQL. Interesting to see that this one is here. So is it part of Delta itself? Yes, so this is part of Delta itself, but it's coupled with Apache Spark SQL. Alright, this is an interesting point to see. So what you do is you use to query the current state of the log as well as modify it by adding new atomic collections of actions. Internally, this class implements an optimistic concurrency control. So optimistic concurrency control means that we are optimistic that there's not going to be any collision when we have two writes into one file. There's not going to be any collisions, and somehow sequentially, in a magical way, it's going to, we'll perceive it as sequential and not concurrent, and we won't have to make a choice. We hope. We're optimistic. To handle multiple readers or writers, any single read is guaranteed to see a consistent snapshot of the table. So this is the most important part here, consistent snapshot, which means using an optimistic concurrency control, this is an algorithm we're picking to choose, everyone who read the table is going to have the same snapshot. So this is how we promise, this is how we make sure the data is guaranteed. This is the data, and everyone who looks at it sees the same data. And this is hard consistency when we talk about consistency levels of data. So this here talks about hard consistency. Alright, so it holds the log path, the data path, the clock, some clock because it holds timing inside, checkpoints, it extends checkpoint class, and it adds metadata cleanup, log store provided, snapshot management, and reach checksum. Okay. Alright, so what is the clock? Clock is lazy implicit val. So this is a val that we're getting when we starting this class. We're getting it from somewhere because it's an implicit val, and it's lazy, which means it's not going to get a value immediate, and it's okay if it will take time to start the clock value here in the class. This is what lazy means. And volatile private delta, so it means it's only accessible from delta. Async update task future. Okay, this is some future. Spark session active. This is interesting. Okay. And store used to read and write physical logs, files, and checkpoints. Create log store. Okay, let's see what this one does. it takes the Spark context from the Spark session. So a lot of you folks, if you've been using Spark before Spark version 2, you're probably familiar with the Spark context. And after Spark 2.0, there's a new object named Spark session, and the Spark session encapsulates the Spark context itself. However, some of the lower level functionalities use Spark context, and it needs that. So I am curious, here we're checking the Spark context, but this is for the creating log store. And again, the create log store is used to read and write physical log files and checkpoint. Okay, checkpoints are also a mechanism that comes with the basics of Spark. I'm not sure which version, but I'm sure I'm seeing it since 1.2 or 1.4. But anyway, it's there for many, many years. Okay, so create log store, and we're taking the Spark session and we're returning an object named log store. All right, so this is the actual function, which is here. It's convenient. We're providing it the configuration for the Spark context itself, which holds a lot of information, and the Hadoop configuration. So it knows where the file system and all of that it needs to store this information. And it creates a log store, which is get log store class conf key. All right, this is yeah. So this is a string, and it defaults log store classes. Okay. Interesting. So it gets some parameter from the Spark configuration and it stores it here. No, it's not what I want to click. All right. Oops, sorry. And then we have, so this is the log store class name. So it basically takes from the configuration the log store class name. And if it, we can pass it to the configuration using this this key. So get sparkconf.get gets a key, and if we don't give it, if this key specifically doesn't exist and it means there's no value for it, then it will take the default log store class. So this is what this one means. And then log store class goes to util class for name. So after we find out from the Spark conf configuration which is the right store class conf, we can find the class for name, the class itself, using the class for name utils that is part of Spark util. Okay, that's very cool. And now we're calling get constructor on the log store class, which is of type class. All right, so now we're constructing a class on the fly, and during runtime, it's going to be, yes, it takes in the class of SparkConf and the class of the Hadoop configuration I see here, or Apache Hadoop common Hadoop configuration, implements yes, and it creates a new instance of this exact configuration as an instance of log store. And log store here is a trait. I clicked it, but we can see there's a lot of implementations of different log stores, which is interesting because here we actually see how this is dependent on the cloud we are using. So we see there is an Azure log store that is dedicated for Azure, HDFS log store dedicated for HDFS, Hadoop file system log store, local log store, and S3 single driver log store. And if you read my first blog on the first part on fundamentals, you've probably seen that I put there a line saying the timestamp, the clock, and a lot of these things comes from the storage that you're using. And this is how you see there's a tight binding to the storage. So my log store is actually dependent on the cloud provider, or if I'm running on-prem, or if I'm using some cloud provider, public cloud provider, it's going to be here. Awesome possum. Right, so this was creating the log store. And we can see here, by the way, this was a trait, which means it's not actually a class, we can't really run it, but someone is implementing it. And you can see for the log store provider itself, there's a lot of different implementation, like the Azure, DeltaLake, HDFS. Yeah, so we see this repeats. Very awesome. The next thing is direct access to the underlying storage system. All right, and this comes log path, yes. All right, so basically here from the file itself, we're saying, please give me the file system that you're running on, because I know you're a file there, because we already have the log path, and we can call the get file system. Yes, very much straightforward, and it takes the session state and the Hadoop configuration. All right. DeltaLake lock. Here we see we had a reentrant lock to allow us to call lock interpretability. Hard word. Okay, you can read it. Okay, it's good to know that we have a locks here and we're locking the table when we need to lock the table. And we're using reentrant locks. All right, Delta History Manager Container version and commit history, Delta History Manager, right? What is interesting in here? This is another configuration that we can pass on the Spark session itself, so we can actually decide. It basically says this, which is the class we're at. So this not providing, if this is new Delta history, if that's not good enough for you, oh, no, sorry, the opposite. So it takes the Delta log and then the max keys per list. So Delta History Manager takes the Delta log and the max keys per list, which is Delta history per search threshold. Right, so now we're actually passing to the History Manager the Delta history per search thresholds, which is the maximum keys we're going to hold per list, which is how many commits to list when performing a parallel search exposed for tasks. Currently, it's set for 1000, which is the maximum key returned by S3. This is by AWS for list calls. Azure can return 5000. Therefore, we chose 1000 because it's the lowest denominator and they don't want S3 to fail. But if we're running on Azure, it's probably a good idea to set this param to the maximum parallel available, just because it means we can create 5000 parallel search, which means it's going to be much faster. So this is an interesting area to understand how the History Manager works. And actually for Azure, we can return up to 5000. Okay, so if you're working on Azure and you're running it yourself on Azure Kubernetes Service or on Kubernetes, then you can set up these parameters and it will be faster for you when you do a parallel search on the History Manager. Okay, a lot of good stuff. Let's see what else in here. Returns a checkpoint interval for this log, not transactional. All right, so it just returns delta config checkpoint interval from metadata. All right. So this we can't really dig in without understanding what it is first, all right? This will keep it for later. The max lineage length of snapshot before Delta forces to build snapshot from scratch. Okay, so max snapshot lineage length. So how much of the data versions we're keeping in the past? And this comes from the DeltaConf. So this is another thing we should be configured when we're starting running this thing. And I see there's no default value here, so it has to come from the Delta SQL conf, which is something that has to be there. And how long to keep around logically deleted files before physically delete them. Timestone, retention wheels. Right, delta config get milliseconds. Turn 1 week from data. Alright, so this is another configuration that we get. And there's some to do here. There is a race here where files could get dropped when increasing the something. Alright, so there's some issue here and some to do. I'm sure there's some ticket connected to it as well. Timestamp before this timestamp will be dropped from that state. Minimum file retention timestamp. Yeah, this is just a calculation. Assert table ID, so it comes from the metadata. So it comes, if we have the snapshot is null, if not, if the snapshot is not null, then we're taking it from here. And snapshot is something we're getting from corn snapshot, and corn snapshot is something we're getting from get snapshotted init, which is ta-da! This is the init for the snapshot. So load the snapshot for this delta table at initialization. This method uses the last checkpoint file as a hint on where to start listing the transaction log directory. If the delta log directory doesn't exist, this method will return an initial snapshot. So basically, if there's a delta table, just bring the snapshot. If the delta table is not there, then create a snapshot. It's pretty straightforward, right? I'm not going to go over this logic because it actually says what it is. So we were in metadata, and we were at metadata.id, so taking the snapshot there. Oh, but you know what? What happens when there's no snapshot? So what is TAT? If util is testing, test ID. Otherwise, get Java util UUID random. So the ID here is made in random. But what happened? This is a snapshot now, which is very rare. But what happens here? And compute state metadata. No, not this one. Snapshot, corn snapshot, get snapshotted in it. Because I think the one that's random is probably for testing and covering. Seems a little bit odd. Okay, so get snapshotted in it. Get log segment, start checkpointing version. Mapping, get or else, starting from checkpoint, or else there's no checkpoint. And the snapshot creates snapshot. Segment, minimal file retention, segment, last commit. What this create snapshot does. What are you doing here? Yeah, it's not clear on where the ID is coming from. There's log path, segment version. So snapshot. Alright, segment version. But it was the metadata, the timestamp checks. It's not exactly the object we're looking for. Alright, we'll have to keep that in mind. It might be that it's a random, but I don't think so because it doesn't make sense. It's usually something that ties back to the system or somehow. So we make sure there's no collisions. Alright. Assert removal. This is nice. Composite ID. Combine the table ID with the path of the table ID to ensure uniqueness. Alright, now it makes more sense that this is random, because what is the chances that when I'm combine the table path and the table ID that I'm getting like the metadata ID, then there will be collision. This is less likely. And so this makes sense much more This normally table ID should be globally unique. So here it is. But nothing stops users from copying a Delta table directly to a separate location where the transaction log is copied directly, causing the table's ID to match. When user mutate the copied table and then try to perform some check joining two tables, optimization that depends on table ID and log may not be correct. Hence, we use composite ID. Now this gives you a lot of information here, right here, that don't copy the Delta table the way it is, because it's strictly bounded to the path. And so if you just start copying it, there's going to be collisions. So this is a very important statement to familiarize yourself with. Composite ID. Okay, so this is how it does that. And lock interruptibly. Yes, so lock without with interruptions. What does it do here? Try body. Where are you, body? Oh, it's just a function. Okay, this is some functions that it's running. Optimistic transaction. Update protocol. Get changes. Protocol validation. Yes. Table exists, is the same log, and short log directory exists. Integration. Alright. So what does it mean when it returns a data frame and it's integrated back into Spark and we want to work with that data frame? So containing the new files within the specific version rate. So when we're running create data frame, it takes in snapshot, add files, is streaming, because we need to know if now we're working with streaming or not, action type optimization, action type itself. Oh, sorry, here it is. So let's start from here. Action type optimization, get or else. If it's streaming, then it's streaming. If not, this is batch. So this is the part where it's going to tell us if we're using streaming or batch with our Spark operations when we're creating the data frame. And file index, Tahoe batch file index. Right, it's another functionality. I'm probably pronouncing this word badly, but okay, this is a batch file index. Spark action type, which is batch or streaming. Add files, it's a sequence of add files, and add files is a class with holds path, partition values, basically all the files that we can add. It says what it is. DeltaLog, which is this. Data path, which is path, and snapshot. Okay. And this whole function returns a file index. And what's nice is it guarantees the list of files from a given list of files that are within a version range of data. Okay, so it's enforced the data range, the version range, which is super critical because we want to make sure we're reading it in the right versions. So if there's a problem, we need to go check out this functionality. Relation. Ta-da! Hadoop, our favorite Hadoop file system. Relations, who comes, this is a class that is part of the Spark SQL execution data sources. So now we're creating the Hadoop FS relation, and it takes the file indexes. Yeah, it holds exactly where we need to start reading, matching files. So that's one we looked at before. And partition schema, that is taking from the snapshot metadata partition schema. And this is basically a struct type of the schema itself in an array format. Sorry, in a structured type format. Data schema. This is a schema, and it's option, mapping, get or else, struct type. Okay, this is also a struct. It returns back, you can see it here, a struct type that has things on it, or get or else. If it's null or empty, it returns struct type with nil, which is a little bit like null, but not exactly. Bucket spec takes none. This is the Scala none. file format from the snapshot, snapshot metadata format option, Spark. So this here file can be Parquet, CSV, whatever file format I'm working with. Format options, and of course it takes a Spark session, so we'll be able to communicate. And on that relation, data set of rows takes the Spark session. Logical relation, we'll see what it is, but it's of rows asks us for Spark session and logical plan. And logical plan, I don't know if you've seen my previous sessions, but it's part of what the Catalyst job is to, well, it's not only from the Catalyst, but it's actually how we're going to operate on the data frame. What is the logical plan to start running on this? So if we're going to join, filter, or whatever operations, and also where are the files, where are we going to read them, where we need to access, etc. What the schema, structure, it's, you know, it's very deep into the Spark core. However, is streaming, and the default here is false. Alright, so the logical relation is an object that's part of data sources. Cool. And this is how it creates our dear data frame. We want it. Let's see what else. Oh, delta logging. What exactly delta logging does? Convenience wrapper for logging that includes delta-specific options and avoid the need for pre-declare all operations. Metrics in delta should respect the following convention. Tag should identify the context of the event with shared user table machine. All actions initiated by the user should be wrapped in a record operation so we can track usage latency and failures if there is a significant rate. Okay. So it's extend delta progress support. So I'm assuming it's like one of the loggers that they're using. Understand functions use the standard uses log reporting defined. Yes. So often, you know, as coders, as developers, we need some logger mechanism. And here we see there's a trait of delta logging that extends the delta progress reporter and uses the Databricks logging itself built-in. So it uses the standard usage of log reporting. Yeah, so recording delta event, record delta operations. All right, so this is, yeah, dedicated tags. Try to get the data or return some null. Okay, record. Standard logging with specific objects that help us log things in a more efficient, organized way so we can later on load it into our dashboard or read it in the log files in a more organized way. Alright, we create only a single delta log for any given path to avoid wasted work in reconstruction. So there's cache builder. Which cache are they using? Guava. Okay, so they're using cache here and they're using Guava cache. Yeah. Okay, on removal. Yeah, this is a standard logger. It's how to write the log so it will be meaningful and invalidate of the cache, of course, because we need to garbage collect if we need to. Clear cache, filter files, rewrite partition files. Alright, we need to explicitly resolve the partitioning columns here because the partition columns are stored as keys of a map type instead of attributes in the add file schema, and those cannot be resolved automatically. Alright. Cool. This is exciting. So we already discovered a lot of stuff. We already discovered that inside the storage matter, the cloud we run matter, and how we configure it matter. We discovered that we have some configuration we need to do if we want to work with Azure, just if we want to get better results, just because it is already tweaked for S3, which can only run search in parallel on 1,000 I think it was files or records, if I remember correctly, versus Azure that can do it in we can run it parallelly on 5,000. I'm sure we can find more edges and points here that connect us to the dependency of the cloud we are running on. But I think for today, we already learned a lot. We already have a lot of information into what's going on. I'm going to take all this information and formulate into the second blog post, which is a deep dive into the DeltaLake itself, which I'm going to talk about the different optimization that you can do, and also how it looks like, what it builds out of, and how it actually guarantees all it guarantees. I hope you enjoyed this. This is kind of out of the fly, compiling a lot of stuff, looking at the code, but overall I hope you had a good time exploring DeltaLake with me. Hopefully I'll see you soon. Ciao.